Hello, and as a native French speaker, I don't practice English very often, so I hope you will be able to understand what I say. If you don't, well, you can have a nap, or you can try to use the slide to follow me. So the idea is that today we can use NFS, which is old, or we can look for something better. And what something better could do that the NFS doesn't do today. For example, it could have a high availability, which means that if you've got a server that goes down, the clients can still access the data, and you want this without a single point of failure, a SPOF. You want storage clustering, where you can add storage servers to increase your volume storage. You want elasticity, which means doing this without any downtime. You want, of course, POSIX semantics. You want file locking. You want performance. And you want secure communications, which means cryptography. And what do we have to do this? Well, for a long time, a file system used to be implemented in kernel, which means that they were not portable at all, and development cycles were quite long because developing in the kernel is not easy. And recently, we have seen a file system in user space appearing, where the file system is a Unix process, and the kernel is a client for this Unix process. We've got message exchanges between the kernel and the file system, which it's a bit like a microkernel architecture. So what file system do we actually have? Well, we've got Lustre, we've got Hadoop, we've got GlusterFS, we've got ExtremeFS, Ceph. We've got lots of file systems. And if we want to mount one of these file systems, we need either a kernel module for it or a Fuse file system. Some file systems have both the kernel module and the Fuse interface, but more and more we see Fuse file systems. And after looking at a few file systems, it seems that GlusterFS was an interesting target, and it requires a Fuse interface. So the goal of my project was to run GlusterFS, and obviously it was to be through the Fuse interface. So what is Fuse? Initially, it was a Linux-only thing, and it became a de facto standard. Now you have Fuse on FreeBSD, you've got Fuse on Mac OS X. I heard that you even have Fuse on Windows, which is a bit strange. So in a Fuse file system, you've got the kernel, which is the client of the Fuse process. It sends requests to the Fuse file system, and the Fuse file system replies. You've got a message passage interface through a character device called devFuse. You've got a userland library, which is there to offload the basic core so that the file system is not too complicated to write. And you've got free API for the Fuse file system, which seems a bit insane, but it's the way it is. In this diagram, you see how the thing works. So everything starts by a process, for example here ls, which issues a system call, for example here read. It does this through the libc. And once the system call is executed inside the kernel, it reaches a layer which is called the VFS. I'll talk about it a bit more in the next slide. Basically, it's a switch that lets the kernel use a different file system. It can be the X3FS file system, or it can be a Fuse file system. If it's a Fuse file system, we've got a Fuse stub inside the kernel, which will immediately send the request through devFuse to userland. Here, you've got three options. You can have a file system that is directly connected to devFuse. It uses the kernel API. You can have a file system connected through libfuse using either the low-level API or the high-level API. So you get three API. The VFS, so it was introduced by Sun a long time ago. At that time, the idea was to have the ability to use both UFS and NFS. So you can think about it like a standard interface inside the kernel to reach any file system, and below that interface, each file system implements some methods. So for the VFS, you've got some objects like mounts and vnodes. Vnodes represent files or directories, and you've got methods, lookup to find a vnode, open to open it, read, write, which are self-explaining. What about NetBSD? NetBSD didn't have Fuse when I started to look at GlusterFS. It had PUFS. PUFS, which is very hard to pronounce, is similar to Fuse but not compatible. It started when Fuse was not obvious standard. It was not obvious that everyone would be wanted to use Fuse. And it seems that the PUFS is there to stay today because it still has merit as a native interface, because a native interface will always fit better your own VFS than a foreign one. And if you want to add a new feature, you don't have to talk to many people. You can do it within the project. How does it work? Exactly like Fuse. So you've got your process that does a system call. You go to the VFS, which is that we are talking to a PUFS file system, and the request which will reach a user land through dev PUFS. And here you've got only one API, which seems a bit more reasonable. So it looks exactly like Fuse. The name of the device is not the same. It's a DevPUFS instead of DevFuse. The name of the library is libPUFS instead of libFuse. But despite the similarity, it is still very different. The message passing in protocol is different, and the API is different. And at least for PUFS, we've got one API. Only one. So PUFS is there to stay because it has merits. Fuse is highly desirable because today people write file systems using Fuse. So we need to use Fuse on NetBSD. And a first attempt was done, which was called WeFuse, which is a nice pun, which is an implementation of Fuse over PUFS. How does it work? Here, on the top of libPUF, you can have libFuse and libRefuse, sorry, and on the top of libRefuse, you have a Fuse file system using the high-level Fuse API, but it's only the high-level Fuse API, which means that we like two API. So we don't support file systems that use a low-level API. We don't support file systems that use a kernel API, and GlusterFS, which was my own target, does exactly that. It opens DevFuse and talks to the kernel directly without using libFuse. So refuse is not enough, and we need something better. So new project is called Perfuse. The idea is to implement the Fuse kernel API. Once we have it, we can just use the stock libFuse on top of it, and we support everything. How does it work? Here I omitted the first part where you've got LS doing a read system call. I think you understand the concept. And now you see that your request that goes from the kernel to userland through dev PUFS, then through libPUFS, now goes through libPerfuse, and libPerfuse is used by a daemon which goes PerfuseD, and his job is to translate the Fuse request, the PUFS request into a Fuse request, sorry, and to send it to a dev Fuse socket so that the Fuse file system can use it directly through the kernel API or through libFuse using the high-level or low-level API. But there is one small problem because I said it was a socket, and a socket doesn't have exactly the same semantics as a character device. For example, you can open and mount a character device where it's impossible for a socket. You have to use the system calls socket, bind, and connect to use a socket. So we need to cheat a bit and use some defines to wrap Perfuse open, which will do the the socket bind and connect stuff. And we define it as open in the Perfuse header, so that if you include the Perfuse header, the things just work. libfuse was modified so that the change is hard to support NetBSD. So today we can just use the standard libfuse and it works. And later I realized that after all I didn't really needed the diffuse socket, and it was replaced by anonymous socket using socket pair. Here I talk a bit more about the VFS because I need it in the next slides for anyone that didn't heard about it in depth. So the idea is that when we do file system in userland, we translate the VFS operation into request for PUFS or fuse. So the VFS operation starts by obtaining the root vnode, and it's obtained at runtime. And then we use the lookup method to find another vnode. You give lookup the name of a node, and you get a reference on a new vnode. You've got a method that get attribute to set attribute to get the metadata for a file. For example, the mode, the owner, the group, the size, and some self-explanatory method like open, read, write, that will open, read, or write on the file or directory. Here is some pseudocode that show how it works. So you first mount a file system, you get a node, then you use the lookup method on the root node to look up for something that is called foo, and you get inoent because it doesn't exist. Then you try to look up something that is called bar, and then you get a reference to a new node. You can use get attribute on the new node to get the inode number, UID, GID mode. You can open it and you can read from it. Sometimes some VFS operations are not really obvious. For example, in NetBSD, we've got the release operation, which is called at close time. We've got the inactive operation, which is called when the last reference on a file is dropped. And we've got the reclaim operation that the kernel will send when he will not use the node anymore, and that memory should be freed. Linux has only release and forget. It's a bit tricky because, as you can see in this example, after you get the release method invoked, you can still have some read calls that happen. In fact, you close your file and the kernel still has something to read. So the release method, which is called for close, doesn't mean that you will not have a read afterwards. So that just means that we've got to wait for inactive to close files. Now I will make a nice list about funny things that I encountered during this project, bugs and traps. So here is the list. We'll see them one by one. So first, another problem about socket semantics. When I use a socket, it can be of type stream, where it's non-atomic and reliable, or of type datagram, where it's atomic but unreliable. And my problem is that a character device is able to provide semantics where messages are sent atomically and it's reliable. So I couldn't use a stream socket. I tried, it doesn't work because the kernel can split the request into several packets. I couldn't use the datagram socket type because it's not reliable. I'm not sure it has to be unreliable for local communication because the sender could just sleep waiting for the receiver to get the data. But changing that would have been quite intrusive and with the risk of breaking things. So we prefer to implement the sec packet socket type, which is an atomic unreliable socket type, which is exactly what we want. Unfortunately, someone did it, and it was sitting in a bug report for I think 5 years without being committed. So I just had to make the code build again, and we had something that worked. Another problem, which is specific to GlusterFS, is that it makes a heavy use of extended attributes on the server side, and NetBSD has no support for extended attribute. Well, it had some support, which came from UFS1 code, but unfortunately, the thing was very broken, it didn't build, so I had to make it work again. And it used a spares file to store attribute, and with one file for each attribute. So if you want to use another attribute, you have to create a backend file. So I had to add code so that the backend file can be auto-created, so that the thing can just work without the sysadmin creating files every minute. I added support for copying extended attribute and preserving them in the CP and MV commands. And then I had the question, because the code coming probably from FreeBSD used the FreeBSD API, and there is also a Linux API for extended attributes, and we had to choose between the two, and finally I didn't choose, and I implemented both API, which turned to be a good idea, because now porting software is much more easier because we support both. There are still work to be done for extended attributes. We need it in a few other utilities. For example, backup utilities, because for now NetBSD is not able to backup the extended attribute, which is a big problem. So we need extended attribute support in packs, dump, and restore. It would be nice to be able to copy extended attribute over the network using ACP and rsync. Rsync has support for it using the Linux API, so I can do it easily. It's just a build option to set up. SCP is a bit more a problem. I know that macOS 10 implemented it, but it was not propagated upstream. Well, so someone will have to work on it. And there are some commands that could benefit of extended attribute, but I'm not sure that it's wise to do so. It's tar and CPIO, because if you add the extended attributes to the format, you somewhat break the standards that doesn't expect them. I'm not sure what will happen with the binaries that will extract the archive if they don't know about standard attributes. Some other improvements that have to be done, adding extended attribute in UFS2. FreeBSD has it, someone has to steal from them. Better storage for extended attribute. Instead of sparse files, we can store them directly into the file system like we did for Quota some years ago. Here again, someone has to do the work. Another funny bug, it's an unordered list. This time it's about race in get attribute method. As you can see in this diagram, when you send a get attribute, then you write some data at the end of the file, you end up in the situation where the kernel has an idea of the file length. After the write, it thinks the length is 3, for example. And then the get attribute replies come with another value which dates from before the write. And the kernel will truncate the file because it discovered that the file is lower than what it expected. And when the write request replies comes, the file size is extended to 3, but with just zeros between zeros and 3s, and we have lost some data. So the solution of this race is simple. We need a mutex on the size. Another problem, which is probably well known, is DNAME thread safety, or I should say thread unsafety. The problem is that the standard doesn't tell us if DNAME should alter the buffer it is given, or if it should return static memory. Both behavior are standard compliant. some software will assume some behavior, and GlusterFS assumes the Linux behavior, which is to modify the buffer, while NetBSD uses a static buffer. Unfortunately, there is no consensus on a thread-safe dirname _r. So the solution was to just add the dirname code from GNU inside the country directory of GlusterFS. They want the Linux version, just give them the Linux version and don't try to be compatible in NetBSD. Other funny problem, what happens if you call the link system call, which is used to do a hard link, on the symlink? Will you link to the symlink itself or to the symlink target? Here again, it's not specified. The standard will not tell you what is the good behavior. And unfortunately, Linux will link to the target, while all the BSD will link to the symlink itself. GlusterFS, of course, relies on the Linux behavior, and it's a very important feature for migrating data from one storage brick to another when you want to replace a server, so we really needed it. So the solution is to use Linkat, which is part of POSIX extended IP set 2, which is a big family of new system calls which improve a lot of things. And this new Linkat is just like link, but it's with a flag. And the flag can tell if we've got to follow the symlink or not. In the NetBSD 6 branch, we only implemented a partial linkat just to support GlusterFS, and finally in NetBSD 7, we've got the whole extended API set 2 except fexecva that was not implemented because some people were scared about it. It seems it's unreasonable security-wise. Another problem, and it's not the last, but the previous before the last, it's what happens if the pagedaemon takes a nap. So pagedaemon is a kernel thread that is responsible for freeing memory when memory is scarce. And one of its jobs is to take vnodes that have memory, that are using memory, and put them to disk, freeing memory. The problem is that when you want to do this with a PUFS file system is that you will need to allocate the message, so you will need to allocate memory, and memory is scarce. And the memory allocator can sleep, waiting for memory to become available, or not sleep, which means it will fail if there is no memory. And we had some situation where the pagedaemon was able to allocate a PUFS message and sleep for memory. We end up in the situation where the kernel thread that is responsible for freeing memory is sleeping, waiting for memory, which means the system will lock. Obviously, pagedaemon must never sleep, so the solution is inside the PUFS kernel code to check what is the calling thread, and if it's pagedaemon, then we prefer to fail with memory allocation and retry and return to the calling code that it doesn't work instead of sleeping. So what happens? Pagedaemon will try to put a vnode to disk. It will not succeed. It will move to the next vnode, which hopefully will not be a PUFS vnode, and sometimes it will have enough memory to start freeing a PUFS vnode. Last funny problem, it was not a complete list. I've got a lot of funny bugs, but the idea was to give you an insight of the various directions where we went. GlusterFS uses swap context, which is a system call which lets you change the CPU register, and POSIX threads. It's a bit odd because usually you use swap context to implement threads, but here they needed a strange concept of task. The idea is that when GlusterFS will send a request to the network, we've got a context that has to wait for the network reply, and it's a bit bad idea to send the thread to sleep and to wait for the reply, because you need to have as many threads as you have a request, and you've got a lot of sleeping threads. So what they do is that using swap context, they are able to load the context in a thread to restore the situation where they were when the request was sent. And the big question is that threads use a CPU register called the TLS, the thread localized storage, to store the address of the private data for the thread. And should swap context touch this register or not? On Linux, the TLS is preserved, which means that swap context is thread safe. While on NetBSD, it was not very clear. In fact, we had a machine-dependent mess where each port was doing a different thing. So what happened? Well, you've got two threads. One thread that prepare context, the second thread that swap context, and then you discover that both threads suddenly return the same value for pthread self, which means that you are going to crash because mutex logs will not work anymore, and we've got to fix that. So what should we do with the TLS register? Obviously, the behavior should be different depending if the program is linked with libpthread or not. If it's not linked with libpthread, then we do not preserve it. We change it using subcontext. And if we link with libpthread, then we preserve it. We had for some ports an option to make context to decide if the TLS register was to be restored or not. So what I did was adding this option to all ports, and so that the various NetBSD ports no share the same behavior. That's all for my list. I could present bugs for a long time, but I got to finish my presentation. The to-do list. So as I told you, we need to add support for extended attributes in a dump and a restore. We need a better storage for extended attributes, because the current situation is it's just scary, because we don't have any tool to check the integrity of the extended attribute storage. If the file is corrupted, you lose everything, and we cannot save them in backup. So it's a real problem. There are some Fuse features that should be implemented. Fuse negative caching, which lets the kernel know that a file doesn't exist and don't ask every second. There is a mechanism for the kernel to send notifications to the file system. The idea is that the kernel will be able to tell the file system that a given file has been removed, for example. And perhaps there is queues, which is a character device in userland. I'm not sure about this one, because it could be interesting if there were some queues driver, a lot of queues driver to use, but I've not seen many, so I'm not sure that it's worth working on it yet, at least. Here I am. Now, if you've got some question.
It might be a naive question, but I don't quite understand why you had to go all around through userland again. To me, it would seem simpler to say, okay, I got the PUFS implementation, I just clone it, and then I turn it into a Fuse implementation, considering I have some code in FreeBSD or something like that. What could be simpler about going again through userland, implementing a new socket types, making sure it works, etc., etc.?
Well, the answer is that it's always faster to develop in userland than in kernel. In kernel, you crash or reboot, you crash or reboot, it's very long. And here, in fact, there are not many drawbacks to do it in userland, because we are working with a network file system. So performances are most about the network and not about going from userland to kernel to userland to kernel. I have not measured it, but when you have to wait for a network reply, one more system call is not really a problem. No more question?
So roughly, how much code did you have to write for the Perfuse implementation?
So,
how much code did you have to write? How big is the library, the Perfuse library?
How much code? I have to run WC on it. I don't know exactly. I'd say that it's a few thousand lines of C. But it's a very simple code. In fact, you get a fuse request, you create you get a PUFS request, you create a fuse request, you translate arguments. So it's not complicated. Well, it's time consuming when you have to spot a bug, in fact. Because the bug list is not the most trickiest, but it's the one that took me the most time to understand. The thing with page daemon that is sleeping, waiting for memory, has been very difficult to find. From the outside, you just see that the system locks.
I have a question myself. Have you measured the overhead of going back and forth in New Zealand and all that?
No, not yet, but I know that it's nothing compared to going back and work the network.
Any more questions?
But by the way, there have been a heated debate between the people that did the Gloucester FS and Linux Torvald. Linux Torvald told them that their thing was a toy because file system should be in kernel, and the people for Gloucester FS had just this kind of argument that if you have to wait for the network, it's not a problem to do more system calls. There are a lot of questions.
About the differences you find with GNU dirname, BSD dirname, and other Linux-specific stuff, have you talked to upstream about it? Because on FreeBSD, upstream Gloucester FS is themselves working on porting it through FreeBSD, so they might be interested in those feedbacks to be able to fix and have something more portable.
I'm not sure I understood the question. You asked me if I send my change to Gloucester FS?
Or just talk with them about those differences.
I do talk with them, and I've been contributed a lot of portability fixes to Gloucester FS. And today, NetBSD just works out of the box for Gloucester FS. You just have to run configure, make install, and it just works. And now I'm working to pass all the regression tests for Gloucester FS. Another example of communication with the Gloucester FS team is that today there is a NetBSD smoke test when you do any commit in Gloucester FS, so we know that it will not break the NetBSD port. And soon we'll know that the regression test will pass, so yes, I'm talking with them a lot. In fact, I'm a bit Gloucester FS contributor. Thank you for your attention.
No more questions?
Sorry.
Okay, thank you all. And next talk is in 25 minutes.